So reminders before we get into the actual content today. Um, there's an update on office hours. Oliver's office hours on Tuesday have been moved 1 hour earlier. It used to be at 11. Now it's going to be at 10 o'clock. I think there was a message sent out about this on an announcement on Canvas as well. And of course, the other announcement or reminder is about homework 2 that's due on Tuesday. It involves implementing a bunch of perceptron variants and also playing with linear models and the mistake-bound model. Always, if you haven't started yet, I encourage you to start soon, after the class ideally. And there's some discussion on Piazza, and I noticed that there were some issues with the autograder. I think they got fixed. Are people still facing issues with autograders? Timing out, etc. If you haven't heard of it, then you don't have issues or you have not started. So yeah, I mean, we had an interesting discussion in office hours today. I think you have one more office hours or two, one more before the deadline. So please take advantage of that. And of course, there's also the late policy that I don't need to remind you about. Are there any questions? Yes.
How formal did our proof need to be for section 3?
Roughly the same level of formality that I have with my proofs in class. So I don't want you to prove, for example, that 1 + 1 = 2. But at the same time, I don't want you to say the answer is 5 because it's obvious. So a good heuristic is we should be able to see your proof and know two things. One, that how you got to the answer. And in case this is, you make a mistake somewhere down the line, we are able to give you partial credit. And the second thing is you need to demonstrate that you understand what you're doing. So, we can't have mystery inferences that are drawn from no information. Does that help? So this is roughly the same level of formality that I use for the proofs in the class. Yes.
So basically, if we just show our work, how we got to each step leading to the final part, that's good?
Yeah, but don't write stories that are very long. Be concise and precise.
Which, like, showing, like, writing out the math in, like, LaTeX or whatever.
Writing out the math and explaining a little bit of what the math is. Yeah. Yes.
Would the mistake bound learning algorithm, like where should we pause? Like it says like in this slide, like look forever. But should we just pause it like
Which question are you talking about? The theory part?
Kind of yes and like
Could you be more precise?
Because in this slide, like just like it says like loop forever.
Oh, I see. So okay. So the mistake-bound model, technically speaking, goes on forever. Because you keep seeing examples and you possibly make an update or not. But we really don't care about that. If there is a mistake-bound algorithm, at some point you'll stop making mistakes. Even if new examples come in, they'll keep coming in, but you're not going to make mistakes anymore. So really, we are not counting the number of examples that we encounter, but just the number of mistakes. And the number of mistakes are going to, if it's a mistake-bound algorithm, the number of mistakes will keep decreasing, the number of mistakes is bounded. So it will never, that's all that matters. So yeah, it might be an infinite loop. In your implementation, that's not how it works, of course. But conceptually, a mistake-bound learner, that particular learner is defined in the online setup. In the online setup, and this is the usage of the word online that has got nothing to do with the internet. It's online as in it's permanently online, it's permanently active. And the learner permanently keeps waiting for examples. Whenever an example comes in, it makes a prediction, possibly an update. But the only thing we care about is how many mistakes. So you are only counting mistakes. And because it's mistake-bound, I mean, if it's a mistake-bound algorithm, because it's mistake-bound, that will eventually you'll stop making mistakes. And after that, yeah, sure, it'll still be receiving examples, but it'll always keep giving the right answer. Does that clarify things?
Yeah, well, like, what if we want to make it in like a pseudocode? You just like do it like in.
Yeah, just do it that way. Yeah, yeah. The only things that matter in a mistake-bound algorithm or a mistake-driven algorithm specifically, the only things that matter are how do you make a prediction, how do you detect a mistake, and how do you make the correction. If you give these three pieces, then the rest, it fits in the same structure. So you can give those three pieces and say this fits in the standard mistake-driven algorithm, and you loop forever. Does that? Sorry. Other questions? If there aren't questions, I am going to go back to our older discussion on pack learning. In the last, oh, that what happened there? In the last lecture, we looked at this idea of pack learnability. And I stopped at the definition. I'm going to restart. Go spend a bit of time on the definition again, and then pick up from there. The main intuition that we had with pack learnability is that we can't expect our learner to produce a concept that is perfect. Sorry, to produce a hypothesis that is perfect. Its hypothesis might make mistakes on future examples because we only have a finite number of examples. And given that finite number of examples, there might be multiple functions that perfectly agree with this finite number of examples, and you have no reason to pick one over the other. And maybe you pick one and nature chooses something else, and you're going to have a mistake. It's unavoidable. So the best we can do is we can hope that the error is at most some epsilon. Let's not worry about the value of epsilon, but it's not zero. But even that is even that might not happen if you are extremely unlucky. It's entirely possible that your data set that you received, that your learner received, was actually a bad data set. It was not representative of the true distribution just because you got extremely unlucky with your sampler. And so there's a small probability that even this modest expectation of low error is not possible. So there is a probability, let's call it delta, that your algorithm, your learner just fails because you got unlucky. So what pack learning says is we would like to have a probability of at least 1 minus delta of success. At least probability 1 minus delta, your learner will return a hypothesis whose error is no more than epsilon. But just saying that is not sufficient. What is doing that? In order to do that, your learner requires an infinite number of examples. That's not good. What if it requires an exponentially large number of examples? Exponential in what? Exponential in the dimensionality and these error parameters. So what pack learning says is, if a concept does not require too many examples and still can guarantee, if for a concept, a learner does not require too many examples and still can guarantee high probability of success defined as error less than epsilon, then that learner is a pack learner. So with probability at least 1 minus delta, the learner produces a hypothesis that has an error less than epsilon. Error less than epsilon. And to do that, it requires m examples, and that m is a polynomial in these four things: 1 over epsilon, 1 over delta, n, and the size of h. And if this property is true for any choice of epsilon and delta, then we say that this learner is this concept is a pack learnable concept according to this learner. Given only a polynomial number of examples with high probability your learner will produce a close approximation of the true concept. And just to remind you, that notion of error that we have here specifically is the generalization error. It's the probability that on a new example drawn from this distribution, your hypothesis makes a mistake. Any questions about this definition of pack learnable concept classes? And I see that, is my screen sharing working? I think the entire last 2 minutes were not recorded. Can people see my screen? Okay, thanks. Any questions? We'll be spending a fair amount of time on this, so think of questions. And also on Zoom, if the screen sharing stops, please post a message, or maybe my TS can let me know. So we have this definition of pack learnability. I've just essentially tagged a concept class as being learnable according to this definition of learnability. There is some algorithm that can produce a good enough approximation, and it can do that most of the time. But that's not necessarily complete. All it says here is that this algorithm will produce a good enough approximation. But what if this algorithm takes forever to run? What if this algorithm guarantees that it will get you a good approximation of the true concept if your data set is good enough, but it requires an exponential amount of time to run? That's not a good algorithm. So pack learnability also imposes an extra condition called efficient learnability. So the concept class is efficiently pack learnable if it can do all of that and also operate in a time that's polynomial in these same complexity parameters. Yes.
Could the number of examples and the time, even though they're both polynomials in the same sort of constraint, could they be different polynomials?
Yeah, of course.
Okay.
Yeah. Other questions? This is where we stopped at the end of last lecture. And I want to kind of pick up on these two definitions today. These two definitions are not saying the same thing. I hope that much is clear. The first one, in some sense, these two definitions are imposing two different kinds of limitations on a learner that operates on a concept class. The first part introduces what is called a sample complexity constraint. Sample complexity is something that you may not encounter in algorithms in such classes. Sample complexity is essentially asking, given a certain set of samples, a certain data set, is there enough information in this data set that allows a learner to distinguish one hypothesis from another one? Think of the data set as offering clues to the learner about the true hypothesis, about the true concept. So the data set is really a set of clues. Are there enough clues in this set that allow the learner to say that this hypothesis is better and a better approximation than that one? So this is called sample complexity. It's an information theoretic constraint. What pack learning says is, for the concept to be pack learnable, the sample complexity needs to be polynomial in the number of examples, etc., in the dimensionality, etc. In addition to that, we have the polynomial time complexity constraint. And this is just purely a computational aspect. Is there an efficient algorithm that can actually process the sample and discover that hypothesis that is good enough? The second part is really about the time it takes to decipher all the clues and find the right answer. The first part is asking, are there enough clues? The second one says, is there enough time to actually read the clues and figure out this hypothesis is better than that one? And what pack learnability says is both of these are required to be polynomial. These are two orthogonal aspects. Time complexity is something you may have seen in other classes, in algorithms or such things. Sample complexity is something that is in a sense, native to machine learning. This is a question that deals with, this is something that deals with information that's available in your set of examples. And is your set of examples rich enough? Questions? The first point there is associated with this first definition here. And the second point is related to the second part. So something else that's interesting is for your learner to be for your concept class to be pack learnable, we don't get to control which function of the concept class gets chosen to be the true concept. Every single function in the concept class must be learnable. That means that no matter which function f in the concept class is the real concept, your learner must be able to find a close approximation to that concept class, to that concept. That means your hypothesis space should contain a function that is close enough to every function inside the concept class. For the purposes of today's lecture, I'm going to assume that your hypothesis space, if you think of this as H, contains your concept class C. So no matter which function is the true concept, it's inside the hypothesis space. So at least the learner has a possibility of finding the true concept. This is not necessarily true, right? You can always have a case where your hypothesis space does not contain that thing. In which case, if that dot is the true concept, there's no way your learner is going to find it. In which case, you have to live with the error, and the error can be arbitrarily large. But for today's discussion, let's assume that it's contained. Let's assume that your hypothesis space contains every single concept, which means your concept class is a subset or equal to the hypothesis space. This is an assumption that doesn't hold in real life because we don't even know what the true concept class is. But we'll start with this assumption and then eventually get rid of it. Questions? Sometimes this assumption is called, when H and C are the same thing, you call this properly pack learnable. I have not seen this anywhere else, but in case you want that word, it's there. Pack learnability is a sort of a worst case definition. The conditions that pack learnability imposes are required to be met for every single target function f in the concept class. For every function, you must be able to find a close approximation and do that with high probability. And remember that it also does not make any assumption about the distribution of the examples. It could be any distribution over the instance space, provided it doesn't change. So for every single fixed but possibly unknown distribution over the instance space, for every single target function in the concept class, you want your learner to succeed with high probability, of course. So in this sense, it's a worst case definition. Online learning or mistake-bound learning was a different kind of a worst case definition that said, no matter which function is the true concept, so that part still remains. No matter in what sequence the examples are presented. Here, we don't care about that. The examples are not presented in a sequence. The examples are all given to the learner in one shot. The learner does whatever it wants with it, but it makes no assumption about the distribution over the examples. Questions? Comments? There's a question. How could we possibly prove that something is pack learnable in the real world if we don't ever know that what concept class the nature chose? That's a very good question. And I'm hoping that even by the end of today's lecture, I'll be able to prove some of those things to you. That's an excellent question. Okay, so now let's actually look at some proofs. All I have done so far is tell you that a certain class of functions, the concept class, is called pack learnable if it satisfies some properties. Now I'm going to show a sort of a tool that allows us to verify whether some class of functions is pack learnable or not. Today we are going to look at a tool called Occam's razor. Occam's razor for consistent learners. I'll explain that in a minute. And as we go along, we'll look at other theorems that are also called Occam's razor. Depending on the context, they have the same underlying idea, but the way in which we prove things is different. So just to kind of take stock of where we are, we looked at what it means for a theory of generalization to exist. And we just saw the definition of pack learning. And now we're going to, we've defined this part here. We've seen a formal definition of the pack model of learning. And now we're going to use this definition and try to make a formal connection to this philosophical idea of Occam's razor. How many people have heard of Occam's razor? It's a phrase that we use, well, some of us use, I guess. It's named after this person there, William of Occam. And it's a rather simple idea. The idea is that if you have multiple explanations for the same phenomena, choose the simpler one. The simpler one makes fewer assumptions, so it's more likely to be right. There's a Latin quote there if you care. And it's not Occam who invented it. He was neither the first nor the last person to come up with that idea. It shows up in different schools of philosophy all the time. And it's generally valid life advice. But in the context of machine learning, the intuition here is if you have two hypotheses that are equally that equally explain a data set, choose the one that is somehow simpler. Choose the one that comes from a simpler class. We'll prove this. The proof really is going to be about if you do that, your probability of generalizations will be better. And it's a rather simple proof. And there are multiple variants, many different theorems that are called Occam's razor theorem. Today, we are going to look at one specific instance. We're going to look at a version where I'm going to make a lot of simplifying assumptions. The most important one is the idea that you have a learning algorithm that perfectly fits the entire data set, entire training set, meaning it gets zero training error. We call such a learning algorithm. Have you seen such a learning algorithm that always gets zero training error? The decision tree learner. If you have a Boolean function and the data set has no noise, well, the data set has no contradicting examples in it, the decision tree learner will get zero error on the training data. Such a learner is called a consistent learner. The question is, what's going to make a consistent learner fail? When will a hypothesis that is produced by a consistent learner fail on a new example? It will fail on new examples if the training set is not representative of the future. Imagine that your training set is massive and is drawn from the same distribution as as generalization examples. So if that happens, your consistent learner might actually be right most of the time in the future. Your consistent learner will have very high error on future examples if your training set is not representative. If your training set is not good, as a result, even though the learner produced a hypothesis that's consistent with your training set, it's not going to do well on future examples. So the hypothesis that is consistent with an entire training set can fail on a future example if your training set is not good enough. If your training set is not representative. It's not sampled in the same way as the test set. That's a bad situation. So what we can do is we can ask, how can we quantify the probability that this bad situation occurs, where your data set is not representative? That's failure. So we can ask, what's the probability that learning fails? And then we can ask, I have an expression that's the probability that learning fails. Let me make that small by bounding it on top. Let's see what I require from my training data if I demand that the probability of bad situations should be low. And this analysis will lead us to a sample complexity bound. That's the plan. We're going to go through this one step at a time. But any questions about this general idea that a consistent learner fails if your data set is not representative? I can see you're all eager to see where this is going. One person is. So let's humor that person. I am. Let's formalize this idea of Occam's razor. And to do that, I'm going to first prove a certain claim. Imagine that there's a certain hypothesis in your hypothesis space. So I'm going to explain this claim before proving it. So let's say your hypothesis space, this is your hypothesis space H, and there's a certain function little h inside that. Think, when I'm saying this, think decision tree. There's a certain tree in the set of all possible decision trees. This hypothesis is consistent with M examples. What I mean by that is you have a training set with M examples, and your decision tree perfectly agrees with every single one of them. It produces the right label on all of them. And yet, suppose I tell you that that particular tree, that hypothesis has an error, the generalization error, that is high. It's more than some threshold epsilon. Epsilon is my criterion for deciding whether this is a good classifier or not. And even though this hypothesis was produced the right label on M examples, its error is going to be more than epsilon. And by my criterion, it's bad. The claim here is that the probability of this situation happening, the probability of having a consistent hypothesis that is still bad, has to be less than the size of h times 1 minus epsilon power m. And I'm going to prove this. This, just to kind of remind you, we are assuming consistency here. We are assuming that your learner is a consistent learner, meaning that your training error is guaranteed to be 0. Later on, we'll drop this assumption, but just for today, we're going to assume that. So the event that you have a consistent learner that is still bad has a probability less than the size of h times 1 minus epsilon power m. H is the hypothesis space, and notice that I have size of h here, which, can someone tell me what I have assumed to be able to write that? Yes.
That H is a finite space.
Exactly. And I have another assumption, assuming consistency plus finite hypothesis space. That's another assumption that we'll get rid of eventually. But for today, we have two assumptions: consistent learner and finite hypothesis space. Okay? Are we ready for the proof? Is the statement of the claim clear? Thank you for saying yes. So let's say that we have this hypothesis H. The error of this hypothesis is more than epsilon. But we know the definition of the error. The definition of the error is simply the probability that this hypothesis disagrees with the true function. I've not introduced f in this slide here, but f is the true function that we don't have access to. So the generalization error is simply the probability that your hypothesis and the concept disagree. And we we know that that particular hypothesis is bad, so this quantity, error D, is going to be greater than epsilon. Just by definition, just by the statement of the problem. If the probability of making an error is more than epsilon, that means the probability of getting the label right is less than 1 minus epsilon. Right? So right, I've done nothing particularly fancy here. This is just your standard idea that either this or this has to be true. Okay, so let's I've just said the same thing here differently. The probability that it does not make an error on an example is the same as saying the probability that H is consistent with one example. The probability that H is consistent with one example is less than 1 minus epsilon, just from the assumption here. Okay? So that's one example. So the H is consistent with one example with that much probability. But we know that the training set has m examples. So the probability that your hypothesis is consistent with m training examples is less than 1 minus epsilon power m. The probability it's consistent with the first example is less than 1 minus epsilon. The probability it's consistent with the second one is 1 minus epsilon, and these two things are independent of each other. So you can keep multiplying them. Questions about this before we move to the next step? Thumbs up? Okay. I was told that I should wait for everyone to respond, or at least half the people to respond. I'm afraid I'll keep waiting forever. So I'll take you as a representative for the entire class. So this is about this one particular bad example, bad hypothesis. The probability that this particular hypothesis is consistent with m examples is less than 1 minus epsilon power m. But the learner need not pick this example. Maybe it picked a different one. Sorry, this hypothesis. The learner need not have picked this one. It may have picked a different one. It has many hypotheses. So let's just, as an illustration, let's say your hypothesis space only consists of 3 functions. And your learner could have chosen any one of them. And any one of them could have been bad. We never know that. We can't tell upfront which one the learner is going to pick before we see the data. So maybe this H1 is consistent and bad. So maybe the probability that it's the probability of it being consistent with m examples is less than 1 minus epsilon power m. Maybe the same thing is true for this one or this one. Right? And your learner could have picked any one of those. The probability that there exists a hypothesis among one of these 3, the probability that one of these 3 things has, is consistent with your m examples and has an error greater than epsilon, because maybe that one got picked. The probability that only one of these 3 things has that thing is less than 3 times 1 minus epsilon power m. There are 3 functions. Probability that one, you just add them up. If you have 3 hypotheses, the probability that one of these 3 is consistent with m examples and yet has a poor generalization error is less than 3 times 1 minus epsilon power m. If you have 4, it's less than 4 times. If you have size of h hypotheses, then you just multiply with size of h here. This is nothing but an application of the union bound of probabilities. If you have a set of events, each of those events is this hypothesis gets picked or that hypothesis gets picked and so on. If you have a set of events, then the probability that at least one of them happens is less than the sum of the probabilities of those individual events. Have people seen the union bound before? Maybe not with this name, but something like this. It's simply, if you have 2 things, probability of A or B is less than probability of A plus probability of B. In this case, A is an event that hypothesis 1 got picked, B is the event that hypothesis 2 got picked. So the probability that some bad hypothesis exists inside H and yet is consistent with M examples is less than the size of H times 1 minus epsilon power M. And that proves the claim. Yes.
Should not be less than or equals.
Yes, you're absolutely right. Questions? Here it's less than equal to, but because, yeah, I've been playing loose with less than or equal to and less than here, and doesn't really matter eventually. Any questions? Ask me questions here. And I firmly believe that the right way to learn anything mathematical is not by watching someone show it on a slide. The right way to do it is you work it out yourself. So you don't have to ask me questions right now. Try to work it through and then come back later also. Yes.
That is based on the principle of intersection.
Here? No, it's actually from the fact that each example is chosen independently from the same distribution. So you have the probability of H consistent with example 1 is less than 1 minus epsilon. Probability that H is consistent with example 2 is less than 1 minus epsilon. So then the probability that H is consistent with example 1 and example 2. So let me write this a little bit more explicitly here. So probability that H is consistent x1, comma y1 is less than 1 minus epsilon. The same thing is true for x2, y2. Right? But then I can ask, what's the probability that H consistent with both? And here, so this is, let's call this event A and let's call this event B. This is asking A and B. But because A and B are independent events, I can just multiply the right-hand sides. Why are they independent? Was that your question? Okay, why are they independent? Why is the consistency of H with x1, y1 independent of consistency of H with x2, y2? I'll come to you in a minute. This was an assumption that we made earlier. Yes.
Is there identically independent distribution?
Independent and identically distributed. Every example in your training set is sampled from the same distribution. They are all identically distributed and they are all independently sampled. So what happens with x1 does not influence what happens with x2 or vice versa. So because they are independent, you can multiply the right-hand sides. Your question?
Is the epsilon just an arbitrary value?
Epsilon is just a number between 0 and 1. In the definition of pack learning, we want the property that we care about to be true, namely the polynomial sample complexity, to be true for every single epsilon. So we want the expression, the sample complexity to be polynomial in 1 over epsilon. That's pretty much all we ask for. So we don't say what the epsilon is. That's the, you don't do it in practice because this is theoretical analysis, but that's the way you think about it. Yeah. There's a question on Zoom. Because of Occam's razor, is this the reason why we prefer to choose Gaussian distribution as our hypothesis? So first of all, we don't necessarily always choose Gaussians as our hypothesis. And I don't think it's because of Occam's razor. Um, we end up using Gaussian distributions a lot in defining probability distributions because the math works out nicely. And Gaussians end up approximating a lot of things well enough that it doesn't really matter. I don't think it's necessarily because of Occam's razor. Okay, so we have this notion of a consistent. So just to quickly summarize what we had here. And from here, we can build up the Occam's razor. The probability that there is some hypothesis in your hypothesis space that is consistent with M training examples and yet is actually a bad one. Maybe your learner is not really a good learner. He just tries to find the first thing that is consistent with your entire training set data and gives it back. Maybe it stumbled on this bad one. And maybe that's why learning is going to fail. And what this claim here says is the probability that happens is less than 1 minus epsilon power m. So probability of there exists is less than okay. That's what we proved just now. And the reason this is interesting is because when you're thinking of a learning algorithm, imagine the stupidest learning algorithm. Don't think of something very fancy. A stupid learning algorithm might just go to your hypothesis space and pick the very first thing that's consistent with the training data. And maybe it just picks this bad hypothesis. So the next thing that we're going to do is even such a stupid learning algorithm, let's try to ask, when will it succeed? Even if I have a learning algorithm that just randomly picks a hypothesis that's consistent, I would like it to succeed. What do we define as success? Success. It has error less than epsilon. In other words, what I would like is the probability of finding a hypothesis that's consistent and yet bad. I would like this to be low. If that probability is low, then with high probability, even the stupid learner will succeed. And that's what we're going to do. So we can ask, I want that probability of consistent and yet bad to be small. I want it to be smaller than some delta. Delta is my probability that my learner fails. I want it to be smaller than some delta, but I know that, let me copy this from here so that I don't have to write everything. I would like this quantity to be less than delta. I can't make it, I can't directly operate on that expression there because I don't have a closed form expression. But instead, if I make this quantity less than delta, then automatically this thing becomes less than delta. Right? If I make the size of h times 1 minus epsilon power m less than delta, then automatically the thing in the box becomes less than delta. As a result, my learner will succeed with high probability. So now let's see what happens, what it takes to make that thing less than delta. We would like to make size of h times 1 minus epsilon power m less than delta. From here, all we have is algebra. We have a bunch of expressions that we can manipulate and just derive some bounds on m. So any questions till here before we start doing the algebra? Yes.
The left-hand side. The H is just the size of your hypothesis.
Yes.
Each set, everything in that set.
Not everything. So epsilon is the error target that we wish to meet. Is the we want to find a hypothesis whose error is less than epsilon. And just to kind of go back, what we showed was the probability that some hypothesis exists in your hypothesis space that is consistent and yet has error more than epsilon is less than that shaded thing there. So this thing, the thing in the box, the probability that some hypothesis is consistent with your training set and yet is going to have high error in the future is less than the size of h times 1 minus epsilon power m. And I would like to bound this object. I would like to make sure that that situation does not happen. That's a situation that I don't like, because that is exactly what's going to fool my learner into thinking a bad hypothesis is the one that's the right answer. The power m, oh, m here, right? The power m comes because we have m training examples, and if you're consistent with one example, that can happen with just by chance, with probability 1 minus epsilon. For it to be consistent with m examples, because they're all independent, it's 1 minus epsilon times 1 minus epsilon times 1 minus epsilon. Multiply that m times. This is the discussion here. So you have two examples, then let me zoom in here. This quantity is less than 1 minus epsilon square. And if you have 3 of them, 4 of them, and so on, it's m of them. You get power m. Oh, you don't understand why it's 1 minus epsilon. Okay, that's easy. Maybe I didn't spend enough time on that.
They don't.
No, they don't. But yes, they do. Okay, so let's start with the probability that h is consistent with, let me write it differently. The probability, the error of h is simply the probability that h of x is not equal to f of x. And by assumption, we assume this is more than epsilon. If h of x is not equal to 1 of f of x, then the error is epsilon. That means the probability that h of x equals f of x for any random example that's chosen is less than 1 minus epsilon. It doesn't matter which example you pick, it's going to have a probability of error less than 1 minus epsilon.
So in this case, we don't.
We
You don't set.
We don't care about setting it. No, this is just a symbolic thing where we're going to manipulate this to derive an expression that connects m, epsilon, delta, and the size of the hypothesis space. And then that expression will be the tool that we'll use to prove things. So the reason we have 1 minus epsilon is because the probability that your hypothesis is correct on any one random example, if it makes an error with probability more than epsilon, the probability it's correct is less than 1 minus epsilon. And so the probability it was correct with the first example in the training set is less than 1 minus epsilon. The probability it was correct with the second example is 1 minus epsilon, because each example in the training set was sampled independently from that exact distribution. Does that? Okay, so now we have a concrete goal. I would like to make the size of h times 1 minus epsilon power m less than delta, because if that happens, then I can force the probability of failure to be low. But now let's move this around. I can take log on both sides. Log of size of h times plus m times log 1 minus epsilon is less than log delta. I've done nothing here. I've just applied log on both sides. Log is an increasing function, so the inequality stays the same. If delta is small, then the probability that there's a consistent and yet a bad hypothesis will also be small. If delta is small, right? Because if delta is small, then this quantity is small, this quantity becomes small. That's bounding on top the probability of consistent yet bad. And at this point, I'm going to start just messing with this expression a little bit. We know, for example, that e power x is more than 1 minus x if your x is small enough. And because of that, I can take log on both sides. So if e power x is more than 1 minus x, it means e power minus x. That means minus x is greater than log 1 minus x. I've taken log on both sides. And here I'm using log to the base e, of course. And so that means this quantity here, so if I'm just change this in, that means this is minus m epsilon. So the log size of h minus, so this log 1 minus epsilon is here, is less than minus x. So do you see what I'm doing here? Or should I do it a little bit cleaner? Maybe I should do it a little bit cleaner, right? Yeah. I'm doing half the math in my head. So that's not a good way to. So let's do it a little bit more clean. What I had is log size of h plus m log 1 minus epsilon is less than log delta. Now, I know that e power minus x is greater than 1 minus x. Let me take log on both sides. So minus x is greater than log 1 minus x. This applies, this is true for all x, so might as well just call it epsilon here. Okay, now let me write the inequality again from the right side. Log delta is greater than m log 1 minus epsilon plus log size of h. But now I know that log 1 minus epsilon is, what did I do wrong here? I think I made a mistake in, yes. Now, so far so good. So far I've done nothing. Now, suppose if I have log size of h minus, if it was true, if I have log size of h minus m epsilon was less than log delta, suppose this was true, then I know that log size of h minus m times, let's consider this, this epsilon is multiplied with the minus here, right? So I can take the minus inside. If the thing on top were true, if this was true, then this becomes true. Why? Because I know that epsilon is greater than log 1 minus epsilon. Sorry, minus epsilon is greater than log 1 minus epsilon. If log h minus, so essentially we are making it more relaxed. If log size of h minus m epsilon were less than log delta, then log size of h plus m log 1 minus epsilon will also be less than log delta. This is one sort of a, this is not pure algebra here. This is essentially a little bit of an argument. So I want you to kind of ask me a question here, if this is unclear. And let me write my log a little bit cleaner. And I hope you also realize why, based on my handwriting, I don't want you to submit handwritten homeworks.
Reason we're saying that if the above is true, then the bottom is true because of that above statement we say where negative epsilon is greater than log minus 1 epsilon.
Yes, if this is true, we know that that's true for small epsilon.
Okay.
Because that's true, Then let's just put, I'm going to just start adding a bunch of things on both sides. Then I can put an m on both sides here, right? I can add a log size of h to both sides.
Then if that front term is less than,
If this thing is less than log delta,
then because the left side is greater than the right side, it corresponds that the right side must also be less than.
exactly. You can think of this as a number line. If this quantity here is somewhere here, this quantity here is somewhere here, right?
Yeah.
And now, if I know that log delta sits somewhere here, that means log delta is more than this quantity also.
I see.
One person sees it, but I want other questions. Yes. You can't, you cannot, absolutely not. And that's why this is a tricky argument. Yes.
We're allowed to assume this statement, though, right? Because we're like choosing the delta.
Well, more than that, we are allowed to use the ifs, choose the ifs. We are allowed to do that because eventually when I present this as a theorem, I will put that if into the condition. If these things hold, then pack learnability works. This is a very weak condition, but even here we get interesting results. It's actually a very weak condition, turns out, because we are making all these one-sided assumptions, one-sided choices like you just described. I'll move forward. I want you to think about this a bit more. But so essentially what we're doing is we can use log 1 minus delta is less than negative epsilon. And this gives us a safer delta, a weaker bound on delta. And so I can write and at this point, I can move things around. Let me just move things around right here since I have written it up. So take this expression. So if log size of h minus m epsilon is less than log delta, then life is good. Let's think of it that way. But then let me just move it around. So log size of h minus log delta is less than m epsilon. I'm just moving the m epsilon to the other side. Minus log delta is exactly the same as plus log 1 over delta. Why did I do that? Because remember in the pack learnability, we cared about the 1 over delta in the definition. We wanted polynomial in 1 over delta. So let's make it an expression in terms of 1 over delta. Okay. It also cared about 1 over epsilon. So let's just move the epsilon to the other side. Right? So we have this expression. If m is greater than that quantity, then this whole thing holds. Yes.
Is there a way to check that if statement? Or is it like, we just kind of assume it holds?
We'll come to that in a minute. I want you to keep that question in your head. When I say a minute, we have 20 minutes. We'll get there. Yes. I'll just write it more. I have already typeset what I just wrote, so you don't have to worry about that. So if m is greater than 1 over epsilon times log size of h plus log 1 over delta, then the probability of getting a bad hypothesis is small. Let's kind of work our way up from the bottom. What we are saying is if m is greater than that expression there, we don't have to remember what it is, but that expression there, m is the number of examples in your training set. If you have these many training examples, then that expression on top holds. The size of h times 1 minus epsilon power m will be less than delta. But if size of h times 1 minus epsilon power m is less than delta, then the probability that you get a consistent and yet bad hypothesis is going to be low because it's less than delta. Delta is a small number. So if you have these many examples, then even your stupid learner that just picks a random hypothesis that's consistent is improbable to fail. Isn't this a cool result? Yes.
So this is tying back to what we were saying earlier about how M should be a polynomial bounded by 1/epsilon, 1/delta, size of H.
And the dimensionality. The dimensionality has not yet figured into this. And there we'll need to know what H is. And we'll have to play with that. Questions about this argument here? Because what I have done here is basically shown you how the proof comes without actually showing you the theorem. Because if you read this paper, you'll see this written upside down. You'll see if this condition holds, then we have pack learnability. What I've done is kind of shown you the way in which a theorem was invented rather than actually showing you the theorem itself. So I see a few heads nodding. I'm assuming up down means yes. So this is the actual theorem. Suppose you have a hypothesis space H. Then with probability 1 minus delta, a hypothesis that's consistent with M training examples will have an error less than epsilon, provided the number of training examples is more than 1 minus epsilon, 1 over epsilon times log size of H plus log 1 over delta. This is the entirety of the theorem. This is not yet a pack learnability theorem because the dimensionality, as you said, does not figure yet. For that, we'll have to actually instantiate H to be something concrete. But this is the tool that we'll use whenever we see a new hypothesis and we are operating in the setting where we have a consistent learner and a finite hypothesis space. This reduces to counting the number of hypotheses. Because if you can somehow count this expression, write that down in terms of the dimensionality, then we are done. Let's unpack the statement a bit. The number of examples you need increases if your demand for accuracy increases. Epsilon is how accurate you want, the amount of error that you're willing to tolerate. If epsilon becomes bigger, because M is greater than 1 over epsilon, if epsilon is bigger, then 1 over epsilon is, sorry, if epsilon is smaller, you want your model to be more accurate, then 1 over epsilon gets bigger. If 1 over epsilon gets bigger, then the sample complexity goes up. You need more examples if you want lower error, lower generalization error, by the way. This is not training error. This is error on future examples, on unseen examples. And that's connected to the question that came up on Slack. How could you probably prove that something is pack learnable when we don't know what the concept class is? Well, because we can. The second term here is an interesting one. It's a little bit unintuitive, so I'll come to that later. Let's go to the third one. The third one says, the third point is about delta. Delta is your confidence in that your learner succeeds. If you want higher confidence that your learner is going to succeed, delta is going to be smaller. If you want higher confidence that your learner will succeed, 1 over delta is bigger, so you need more examples. You need more examples to be more certain that your learner has actually found that a good approximation. Now the middle part, size of H. If we have a larger hypothesis space, then the sample complexity increases. If your learner has to explore a larger set of functions, then it needs more data points to help it explore that set in order to find a good hypothesis. That's an interesting one. If you have a larger set of functions, learning becomes harder. We've seen that before, right? We've seen that intuition before. Here we are saying if your learner explores a larger set of functions and you have only a small number of examples, then your generalization error is going to suffer. You have only a small number of examples and your learner explores a rich set of functions, then you might end up overfitting the training data because you only have a small number of data points and your learner might end up overfitting. This is why this theorem is called the Occam's razor. you should not be exploring a larger set of functions unless you need to. You should be exploring simpler functions. There are fewer simpler functions than there are more complex ones. So you should be exploring sets of simpler functions first before you consider needless complexity. This is why it's better to have decision trees with a depth limit rather than all possible decision trees. The set of all possible decision trees is more than the set of all decision trees with depth 3. So if you found a depth 3 tree is very hard. Depth 2 tree that fits your data perfectly, then there's no reason to consider a depth 17 tree that also fits your data perfectly, because you have a small explanation that explains that is consistent with your data, and because of this theorem, that's more likely to generalize better. Questions? Yes.
Could we also assume that a smaller sort of, let's take, for example, the tree. Could we also assume that the smaller tree is going to be less computationally expensive to?
That's orthogonal here, right? We are assuming nowhere here did we talk about computation. That's the efficiency part of things. Efficiency wise, of course, smaller trees are better. But even if there was infinite compute available, from the perspective of generalization, this is a better deal.
Okay.
So these are the two different aspects of pack learnability. There's efficient learnability, and then there's that sample complexity. This is just about sample complexity. It's called Occam's razor because it expresses a preference for smaller hypothesis spaces. Consider smaller hypothesis spaces before you consider larger ones. Yes.
If we assume that since we are already taking the simple functions and the true function is from the concept class, which has a complex function, so we'll be able to prove this.
No, but here's the thing. That's an excellent question. So let's say that our true function, let's use decision trees as a, because it's a running example. Let's say the true function is a depth 17 decision tree. And your that means that you ideally need to find that tree. But let's say you have a small enough data set where a depth 2 tree has fit the data set. You have no reason to believe that the 17 tree is better, given only the data that you have. Because of this theorem, what you know is the probability that the depth 17 tree is the right one is lower than the probability than for the depth 2 tree, because the depth 2 tree makes is unlikely to fit a large enough data set perfectly if the real tree was 17. You could, of course, we can always get unlucky, and that's why we have this 1 minus delta. You will only succeed with probability 1 minus delta. There's always a delta probability that you will fail, but hopefully that delta is small. Other questions? Yes.
Where does the theorem kind of talk about like so it mentions like the size of the hypothesis space, but it doesn't say anything about like the actual value of the hyperparameters that you use, right?
Sure.
So like where does it, like for instance, you can use a space consisting of high values, but that's restricted, right?
You could. In fact, that's an interesting point. That's a very interesting observation. So let me repeat that. At no point in this theorem do you actually, it does not say anywhere that so let me give an example here. Let's say I have two hypothesis spaces. H1 is all, and H2 is this is a set of two trees. Each of those two trees has 100 nodes. Or let's say this has depth 17 and this has depth 100. These are really large trees. These are really complex explanations. This theorem only looks at the size of the hypothesis space and not the actual, the complexity of the explanation. Essentially what it's saying is the complexity of the simplicity or complexity of hypothesis space is entirely defined in terms of the number of functions that exist. If you have only two trees, the process of eliminating one of them is very easy because you just need to try out each example on each of them, and it's easy to pick one. However, think of the number of trees of depth 100 there exist. You need to have picked one of them up front. How do you know? You've already done the hard part, right? So you've already explored a massive one. Maybe you just got lucky and got the right one, but more likely than not, you got unlucky and you didn't get the right thing here. And so if you actually did get lucky, you've used more information, which means the sample, you have used other data that's not in this set M. So there's some side channel information that you've employed, in which case it's fine if you know that these are the only two trees, your hypothesis space is actually much smaller. And the Occam's razor still holds because this is the complexity of a hypothesis space is simply the number of functions you're entertaining. That's a very subtle observation, but good one. Other questions, comments? Yes.
So I guess delta would be the ratio of the consistent bad learners over the total hypothesis space.
Not quite, no. Delta is the probability that your learner has found a model, a hypothesis, whose error is less than epsilon. So as a ratio, it is the number of times your learner finds if you want to imagine this as a ratio, it's the number of times imagine running your learning algorithm many times on different data sets. And for each one of those, you measure, did it get low error or not? And it's the number of times the learner succeeded or failed actually, because it's delta is about failure. The number of times your learner failed to meet that error threshold divided by the number of times you actually try to do the learning.
Right. So it doesn't seem like delta isn't just some arbitrary value that we can choose. We have to calculate delta.
No, we don't calculate or choose any of these things. In fact, that's a common question that I get. You don't calculate or choose any of these things because we are not going to use this theorem to make any claims about a particular instance, a particular data set. We are going to use this theorem specifically to make claims about hypothesis spaces. All we demand for pack learnability is that the sample complexity M should be polynomial in 1 over epsilon and polynomial in 1 over delta. This already satisfies that. So we are done. Polynomial in 1 over epsilon, trivially, it's linear in 1 over epsilon. It's logarithmic in 1 over delta, which is even better than polynomial. So we are done with delta and epsilon. I'll show you an illustration of what delta and epsilon might be, but we never actually use it to do anything specific. It's mostly to check the boxes with respect to the theorem, with respect to the definition of pack learnability. Sorry.
Right. So I guess the key takeaway for me at least is that we would need to increase the size of the training set in order to decrease the probability
Of failure.
of failure.
Yes, that's absolutely right. In order to, you can rewrite this whole expression and bring delta to one side and M to the other side. And then you can ask, if I want delta to be low, how many examples do I need? You could frame it that way. And what you'll see is that you'll need more examples. So this expression asks or shows what it takes for a M consistent hypothesis, which means a hypothesis that's consistent with M examples, what it takes for it to have low error. It's entirely, going back to the earlier point, it's entirely possible that your true hypothesis, that is the best hypothesis, is a complex one. But the simpler ones are unlikely to fool your training data, fool your learner by being consistent with many examples. If you have only a small set of functions, you are less likely to find one that's consistent with a large enough number of training examples and yet be the bad one. That's really what this theorem says. So from this expression, we kind of get a recipe for proving pack learnability. So if you have some hypothesis space, H, all you have to do is find a consistent classifier, consistent model. In other words, all you need to do is find a hypothesis that perfectly agrees with your entire training data. And I'll come to a question in Zoom. All you have to do is find a hypothesis that's consistent with your training data. And if it turns out that your hypothesis space H is small enough, then without actually doing anything else, you get pack learnability. Small enough is something that we have to work on, and we'll be doing that on Tuesday. Of course, but that's not all. You also need to show that you can actually find a consistent hypothesis efficiently, because remember, there's always a computational complexity aspect that you need to worry about. Question on Zoom is, does it mean that we should choose a much simpler hypothesis if we have less data? That's right. If you have smaller data sets, let me rephrase that comment to be more correct. If you have a smaller data set and you choose a smaller hypothesis space, you are more likely to not overfit. I was careful there. That does not mean that you're guaranteed not to overfit. And that does not also mean that you are required only to choose the small hypothesis space. But if you choose a small hypothesis space, you are less likely to overfit. And that's the intuition here. And that's why it's called Occam's razor. Choose a smaller explanation first. Okay, there are only 2 minutes left, so I'm not going to start applying this theorem. What we will do next is start looking at the size of H, because what we have here is a recipe to prove pack learnability. Given a new hypothesis space, what you need to do is check if the number of functions in the hypothesis space is small enough, and we'll see some details later on, so that this expression here, log size of H, is still a polynomial in the dimensionality. Remember, in the pack definition, there was also a dimensionality term. So to do that, we need to start counting functions. So here are some exercises to kind of help you think about this. We've seen decision trees, right? How many if you have n binary features, think about how many decision trees there are over those binary features. Based on that, you should be able to answer the question, are decision trees pack learnable or not? If not, don't worry, we'll answer it on Tuesday. Similar thing, you can ask about conjunctions. How many conjunctions are there? Are conjunctions pack learnable? How many monotone conjunctions are there? Are they pack learnable? For every class of functions that is finite, using this theorem, you can ask whether it's pack learnable. To answer that, you just need to know how many functions exist. Provided log of that is not exponential in the dimensionality, we are good. We'll be looking at 3 or 4 examples on Tuesday. So I'll see you on Tuesday. And don't forget your homework and such things.